from class last Thursday. I'm going to try to recreate what I did in class. I have almost all of a diary from what I did then, so I'm just going to go through these commands and discuss them as I go. So one thing I want to remind about is first let me start the diary. So that was from the 12th. Okay. I'm calling it diary B because I already have a diary from the first time. This is the second attempt. So I want to give a reminder to everyone about M file names. Since you're going to be submitting those with the assignment, again, don't name a match of a problem. Don't put the problem number in them with the dots and so forth. Certainly not spaces, because some of these are uh, functions, and the function name has to match the file name, where a file name would also have a .m extension tacked on. So M file names, aside from a .m extension, should have only letters, digits, and underscore, and also they cannot begin with a digit. So if the problem in the assignment specifies the name of a function or the name of a script, I need you to use that name exactly, because that way I can run your code if I need to when grading it. Okay. If you're going to be submitting a MATLAB diary with your assignment, which would be a good idea for certain problems, what I prefer in that case is just a .txt extension, because a diary is a plain text file. It's not doesn't really have valid MATLAB code because of all the output that's in between your commands. If Java was stripped out, then yes, you could run it as a script, but that'd be a lot of editing to do. And for the assignment, I want to see both your commands and their output. So just put a .txt extension on those. That way I can open it up and look through it in an ordinary text editor, like TextEdit on a Mac or Notepad on Windows. Okay. The other thing I want to point out, since there are a lot of problems in this assignment, there are 29 in all, but I want to point out I will be assigning each a similar amount of weight. Every assignment is going to be out of 100 points. Now, unfortunately, 29 does not divide 100. So that means that each problem is going to be worth either 3 or 4 points. I'm not going to do fractional points or anything like that. Also, homework is 30% of your grade, and there are 10 homework assignments. So this particular assignment you're working on now is worth 3% of your overall grade. And I'm pointing it out because if you come to a problem where you just don't know how to do it, you end up not submitting it, then what you end up losing. So let's say if it's a 4-point problem, worst case, but that's only the whole assignment is only 3% of your grade. So 0.12% of your grade is what will be lost. So in other words, not much damage done. I also strongly encourage you at least make an attempt. I do like to give partial credit when I can, but if you don't submit anything at all for a certain problem, of course, there's nothing I can do. So please keep that in mind as you work to complete the assignment. Also want to remind everyone of the late policy that's stated in the syllabus, and the syllabus is here on the website down at the bottom. So every day the assignment is late, 5% gets deducted. So the homework is due on Tuesday, September 17th. It can be turned in any time that day. I mean, I'm not going to be checking timestamps rigidly. Like if I wake up to seeing it in my email from you on the morning of the 18th, that's fine too. I won't mark it late at that point. But after that, that's when you risk getting deductions. Okay, but as we saw, 5% of an assignment that's worth 3%. If it gives you a chance to finish more problems than you might have submitted otherwise, taking a late day in that situation might actually prove to be have a net benefit. Okay. Let's see, just looking through the diary here. Some of the things in the diary are in response to um, questions that I got. Okay. All right. So I gotten problems about okay, so the discussion of problem 1.2.11, and I'm going to put that on the screen here so you can see what that is. Okay, hold on a second. Okay. Okay. Whoops, I don't want that. Sorry. Okay, I should need the textbook here. All right, so problem 1.2.11. Okay. Let me make this a little bigger here. Okay. So this is about given a matrix, you write a single MATLAB statement that interchanges two given rows of a matrix. So you can set values for I and j if you want, just to experiment, but you need to submit a statement that would work for whatever matrix A you're given and whatever I and j are given. So in other words, it should involve I and j. So in this case, so like what you would do at the outset is make a random matrix. So I'll just make a 5 by 5 matrix here. And then if I set I equals 1, let's say, and j equals 4. Now, what the matrix should look like, so here's the original matrix. So if I wanted to swap, I have the same matrix except rows 1 and 4 are swapped. That'd be row 4, then 2, 3, 1, 5. So we have indices 1 through 5, except that I've switched 1 and 4. And then these are my row indices. For columns, I just want to take all columns. So the result of your statement would be something like this. Notice rows 1 and 4. Look at the entries here, 9866 and 7730. Those have been switched. But the thing is, your statement that you would submit for this problem is an assignment statement. So perform something equals something else. And the reason that is, it has to be that way, if we look back at the problem, it says the statement overwrites these rows of A with the interchanged rows. So you have to have something on the left side of the equal sign that is those two rows, and then on the right side would be those rows interchanged. So you can assign two rows of A to something else that would also be two rows of a correct size. Like here, A is a 5 by 5 matrix. So if my left side of the assignment extracts two rows of A, each has 5 elements, I can assign to it a matrix that consists of two rows, also each one having 5 elements. So as long as the size is matched, then the assignment is valid. Okay. So what I just did here, this statement, so the statement above, displays A with rows 1 and 4 swapped, but A does not change. So if I were to call up A again, I would just get this, because nothing I did here, all it does is displaying the rows in a certain order. It would not do anything to change A. So your assignment statement for this problem will work with only rows I and j of A, because the other rows are not affected in any way. Okay. All right. So to give you an idea how you modify a portion of a matrix, so I'll do something different than the problem that you're assigned, but what I'm hoping is it gives you an idea of what you have to do. So for example, this matrix A here, suppose I want to set the first row of A to 0. I can do this, A1, row 1, all columns equal to 0. So watch what happens here. And sure enough, well, this is the original matrix that we compared to, and now all those entries in the first row have been wiped out. So that affects only the first row. Okay. Now, what we'll do here is the conclusion of the MATLAB tutorial. So the next section of that will deal with graphics functionality. So what I'm going to do is there's a problem in the assignment where I have a graph in the book, a plot in the book that shows graphs of three functions or powers of x squared, x cubed, x to the fourth, plotted in different styles. And the problem is to reproduce that plot, because in the book I've not given the commands to do it for that specific case, but I do describe the commands that you would use. So we're going to take a look at those right now. So first, what I want to do to show how plotting works is I'm going to create a vector of x values in -1 to 1. So that'd be x goes from -1. And you're going to use a fine spacing here, 0.001. Should work. Okay, so, and I'm transposing just so I can make it a column vector. I just prefer column vectors. Now, I want to plot a function y equals x squared versus x. So you might think, okay, I'll just set y equal to x squared. And it does not like that. So the exponentiation operator, the up arrow, can only be used on a square matrix, which would include a 1-by-1 matrix that's just a number. So only for those cases. But if you have something else, like a vector or a non-square matrix, and all you want to do, well, powers of those are not really mathematically defined. However, if you just want to raise each individual entry of that vector or matrix to a certain power, that you can do with just a slight modification. Notice the error message is pretty helpful here. Use the dot up arrow for element-wise power. That's what I want to do. I want to take every element of x and square it, and that goes into y. So I'll do y equals x dot squared, and that works. It takes it. So now I'm going to plot y versus x. So that's the simplest usage of a plot command. You have a vector of x values and then a vector of y values. They must be the same length. Also, they must be the same type of vector. They can so both row vectors or both column vectors. Now, you can pass a matrix to plot. If you do that, it will plot each column of a matrix and put them on the same plot. But for simpler usage, just plotting x, y values. Okay, so a figure comes up, and we see the familiar parabola, y equals x squared. Now, I'm going to do some annotation here. So to annotate the graph, I want to label the axes. So I could do x label x in quotes, only single quotes. Remember, MATLAB uses only single quotes. And then y label y. Okay, and let's take a look at that. So I have, we see a little x here for the x-axis. On the y-axis, we have a y that's rotated 90 degrees to label the y-axis. Now, I'm going to, now here we have a solid curve, but really what it is it's many, many points, because if you look over here, my vector of x values, because I use such a small spacing, has 2001 elements. Really, it's 2001 points that are plotted here, and then MATLAB connects the dots. So that's the default, is to plot the points in blue and connect them with blue line segments. And because those line segments are so small, it has the appearance of a smooth curve. Whereas if I had used fewer points, like maybe just 10, it would not be a smooth curve. We'd see kinks at each point. Okay, so what I'm going to do now is I'm going to plot another function. I'm just going to plot y equals x. So plot, actually, no, sorry, I'm not going to do that. I'm going to plot x squared again, but I'm going to plot in a, okay, no, actually I do want to do y equals x. So, so I'm going to plot x versus x. We're going to see a line on the graph, but I'm going to use a different plot style. So there's an optional third argument where I can specify different plotting styles and colors. So R for red, and the double dash here indicates plot a dashed curve instead of a solid curve. So if I go ahead and do that, so now we see a red dashed line here for a function y equals x. But notice everything else that was here before went away. My axis labels went away, and most of all, y equals x squared went away. So that's how plotting in MATLAB works by default. That when I plot something in a certain figure window, if there was something already there, it's wiped out. So what you can do if you want to keep what's there, like to superimpose several curves in the same plot, which is what's called for in the problem in the homework, to reproduce that given plot, I can use this command, hold. Now, hold by itself toggles what is called the hold state. So by default, hold is off. That means each plot wipes out the previous plot. Hold on means the previous plot is retained. So I'm going to say, so I could say hold, but I'm going to say hold on, because I think it's a better habit to get into, because then you know exactly what the effect will be. So, so now the whatever I plot here, this red dashed line is going to stay. So now I'm going to plot another function, plot x versus cosine x, and I'm going to have black circles. So the k means black because b is already taken up by blue. So if I do that, so the red dashed line is still there, but now we have this. It's 2001 circles that are plotted here. And that's why it looks like such a thick, smooth curve here, just because there's so many points. Now, this doesn't really show what it's like plotting circles, so I'm going to show you how to delete this curve. If I click on the arrow here, so the select tool, notice these symbols here, it says that the whole plot is selected, but I want to select, like I could select this line. Notice you can see it's selected, but I want to select this one. I don't know if you can see the little blue boxes here to indicate it's selected. And then I can just hit the delete key, and there, it's gone. So now what I'm going to do is I want to create another vector of x values between -1 and 1. There's fewer x values, so I'll just do x2 is -1 with a much larger spacing, 0.1 to 1. So now I have x2, which has only 21 elements in it. So now I'm going to plot x2, cosine of x2, again with black circles. Okay. And now we see, so now you can see each individual circle. So that's what it's like to plot with different styles. So the default is a line, but now you can plot circles or other symbols like pluses, x's. So if you use the help page for plot, it shows different colors and line styles and markers that you can use. But also you can change these things from within this figure window. So if I go ahead and select this curve and I want to make changes to it, for example, I can do marker size. By default is 6. But I want to make it a little bigger, let's say 12. Okay, so now those markers are a lot bigger. If I go ahead and select this line, we have the line width by default is 0.5. I'll pick something thicker, so 4. So now it's a much thicker red dashed line. Okay. Now, I've shown you how to label the x and y axes. I can also put a title. So the title command, you pass a string that's the title of your plot. So playing plot. Okay, and that will display the given title at the top. It's kind of small here. So I'm going to make everything, the text here, a little bigger, just so it's easier to see. And this is actually a good idea for if you're going to use a MATLAB plot in a presentation, like something that's going to be shown on a screen of a projector, like I normally do in class. If I go over to the main MATLAB menu and choose Preferences, then I select Figure Copy Template, and there's two modes of display. There's Documents, so that I would use the default settings, preferably, and then Presentations. So a lot of things happen here. It changes the font size, makes it bold, makes the lines thicker, although I already did that. So I do Apply to Figure, and then if I, okay, then okay. So now notice that all of the text is larger, and it's also bold. So it's much easier to see on a screen. So if it's going to be in a presentation through a projector, it's important that you do that. Okay. Now, other commands that you can use, and this will be helpful to you in the homework. The legend command is used to identify whatever curves you have. So the first function I plotted was just y equals x, and the second one is cosine. So I list them as arguments to legend in order. So keep in mind the order in which you plot things, because that's what legend goes by. And it puts this little legend here in the upper right, but you can also move it if you want. So notice the first thing I plotted was y equals x, so it uses whatever line style and a marker that I used for x, and then also for cosine. And if I want to, I can move this around. I can also make it bigger. Although it doesn't grow the interior content though. So that'll be helpful on one of the homework problems related to graphics. Yet another command, if I do gtext. So once I hit enter, then I have this crosshairs in the screen, so I can decide where I want to place this text. So I'll just move around a little bit, and as soon as I click, that indicates the lower left of where that text goes. Now, I've made it pretty small, but if I want to, I can see if it'll let me make it bigger. Okay, no, okay, it'll only let me move it. However, what I can do is I can make it bigger by selecting font, and see we have this font selection, what font weight, italic or bold, and also the size. So right now it's size 10. I'll make it 24. Okay, and that text is a lot bigger now. And but even after I've placed it through gtext, I can move it around. Now I'm showing you plot. That's for two-dimensional plots. There's also a plot3 command for three-dimensional plots where you specify x, y, and z. Much of the usage is the same, but like if you could do x label, y label, z label for the axes. But gtext is only for two-dimensional plots. Because you're projecting the three-dimensional, you're projecting 3D in a 2D space. So it wouldn't know how to associate where you click with a three-dimensional point. Okay, now everything I've been doing is shown in Figure 1. But I can have many figure windows. So if I just do the figure command by itself, it creates a new figure window, and it'll use the next number available, so in this case figure 2. But I can give it whatever figure number I like in the figure command. So I could do figure 10, and now I have figure 1, 2, and 10. So 3 through 9 are missing. Now I can do also in figure 1, I have one set of axes in this window, but I can have multiple sets of axes in a figure window arranged by arranged as a matrix. So if I go back to like figure 10, so I'm going to divide this into several um, subplots using a subplot command. So a subplot command, you specify how many rows and columns you want for your axes. So I want a 2 by 3 matrix of axes. And then the third argument is which one you want to be active. So I want the first one, which would mean and they're ordered from left to right and top to bottom. So now I have one set of axes here in my two row 3 column matrix. So they're numbered 1, 2, 3, 4, 5, 6 for referring to them in the subplot command. So now whatever plot commands I make will go to this set of axes until I select another one using subplot. So for example, I could do plot x and then e to the x. And there's that curve there. But now what I'll do is select a different set of axes. Subplot, still 2 rows, 3 columns. Be sure to keep these the same. If you change them, then it'll wipe out what was there before. So use this command carefully. So I'll select plot number 2. So now I have this set of axes here, and I can, so whatever I do next for a plot command will go here. Now, I'm going to show you one particularly entertaining use from some years ago of a subplot command. Okay, so I need to go to my browser for a second. Okay, so I have all right. So some of you may have seen this at one time or another. Mathematical dance moves where the arms depict certain functions: sine, cosine, x squared, and then crap here. So several years ago, when I was teaching the second class in the sequence, Math 461, I sorry, excuse me. So a student had shown me this and then made a remark about it'd be nice if we could create something like this in MATLAB. And I took it as a challenge, and I'm going to show you the result. So I'm going to go to a different directory here where I have this old code. Okay, I'm going to delete this. That was created in the previous in last class. So it's a math dance. Okay. So it takes as arguments a cell array that's indicated by the curly braces of functions. I'll talk more about function handles a little later. And then another cell array that indicates text labels for these functions, so sine and cosine. The @ sign indicates the function handle, but as I mentioned, I'll talk about that later in the tutorial. So if I go ahead and run this. Oh, okay. So yeah, use a subplot command over this, so wiped out what was there before. So what we have here is the functions sine and cosine. I multiplied by certain factors like positive and negative to make the arms move up and down. I used I constructed a polynomial, a 4-degree polynomial for the body, polar coordinates for the head, the eyes, and the mouth. I used actually during class on Thursday, I made the eyes red by editing the code to do that at the student's request. Also, if you notice, the eyes actually they move from left to right, so I changed the origin of these circles with each step, with each plot, and then also change the radius to make the eyes grow bigger than smaller. And sorry if that looks creepy. One set of arguments I found more entertaining is instead of sine and cosine, I use tangent and exponential because the vertical asymptotes for tangents, and then the exponential growth gives this figure a extremely long left arm. But yeah, you can see the eyes growing in size and also shifting. So really creating multiple plots, like 30 or so, and it also writes a video file. I'll post this code afterwards that created this, so you can take a look at it. Okay, but this is a use of subplot. I have it in this case because I have two functions. I have a 2x1 matrix of plots put next to each other. Okay. Now I'm going to. So this command close all gets rid of all open figure windows. Actually, I want to change back to my tutorial directory here. Okay. Before I move on from graphics, I just realized there's one other thing I want to show you that wasn't in my diary, so I almost forgot about it. If I go back to, okay, I'm going to close this one and this one. I want to go back to figure. Oh, okay. I need to. Well, I ended up closing everything anyway. So close all. In this case, would do nothing. But close all. If you have figure windows, it just wipes out all of them, so it reduces some clutter. But I'm going to go back and recreate an earlier plot. So plot x function y equals x with red dashes. Okay, and then hold on, and then I'm going to plot x2 cosine x2 with black circles. Okay, so suppose I want to save this to an image file. So I can do that using save as. And I can call it functions, and I'm going to pick an image format. You see there's several here, JPEG, PNG. I like PNG for the vector graphics. So in this case, it's going to complain that the file already exists and ask if I want to overwrite it, and I do. But notice once I hit replace and therefore tell it to save this image, notice it flashes white for a little bit. That means it's actively writing the file. So wait till it goes back to normal before you close this. But one very important point to make about saving MATLAB figures. Notice I always use save as instead of save, so I know exactly what format I'm saving it in. So MATLAB figure .fig. So the advantage of saving as a .fig is that if you close your MATLAB session and then come back to MATLAB later, you can always open the .fig file and keep modifying the figure. Like suppose you realize, oh, you have a wrong axis labels, or maybe you put this figure in a paper and or a presentation and found it didn't look quite right. Maybe you needed to make curves thicker. If you save it as a .fig file, okay, I'm overwriting it again from class. Then it will. So like suppose I close this down. So now I can go over here to functions.fig and double click on it, and it'll open it again, and I can continue messing with it. So for example, I can go back and change the axis label. Like suppose I forgot it before, and then I can go ahead and save it again in this fig file. And if I want, and then if I want to update an image, I can do a save as then. Always save the .fig file in case you need to go back and make changes. That has saved me so much time in the past when putting figures in papers and presentations and such. And figure files, most of the time, not always, depends on what you're plotting, don't take up that much hard drive space. So it's definitely worthwhile to make a habit of. Okay. Now, moving on to the next section. I'm going to close everything down here. Polynomial functions. And we're going to look at a few of them. And you can use help polyfun at the prompt to get a list of all of them. Now, how polynomials are represented in MATLAB by convention. So it's a good idea to follow this convention if you write your own functions that deal with polynomials, and actually in later chapters you will. They are a row vector of coefficients arranged from highest degree to lowest. So, for example, if I have a polynomial x squared minus 5x plus 6, so I'm going to make a row vector called p that has the coefficients of this polynomial. 1 for x squared, and then minus 5 for the coefficient of x, and then 6 for the constant term. So MATLAB will interpret that as a polynomial x squared minus 5x plus 6. So the first function I'll show you is roots. So r equals roots of p. So that will compute the roots of this polynomial and output them as a column vector. So of course, this factors into x minus 3 times x minus 2. So sure enough, the roots are 3 and 2. If I want to work with one of these roots, like if I have roots x1 and x2, if I want to call them that, I can say x1 equals r of 1 and x2 equals r of 2, and then I use refer to the roots that way in subsequent statements. Now this works whether the polynomial has real or complex. So for example, if I make a polynomial 104, so this is x squared plus 4, and I need the 0 in there, because if I just have 1, 4, MATLAB will think that I mean x plus 4, but I mean x squared plus 4. So x squared plus 0x plus 4. So if I do the roots of p, so the roots are plus or minus 2i. So whatever roots there are, because any polynomial degree n has n roots, including multiplicities that may be real or complex. Okay, so that's a roots command. The next command is poly. Poly goes the opposite way of roots. So roots, you give it the coefficients, it gives you the roots. Poly, you give it to roots, and then it will give you you give it to, sorry. Roots, you supply the coefficients, it computes the roots. Poly is the opposite. You supply the roots, poly returns the coefficients. So here, it's going to give me the coefficients of a polynomial that has factorization x minus 3 times x minus 2. Sure enough, that's x squared minus 5x plus 6. Now, with poly, the leading coefficient will be 1. So I could, because if I want a polynomial that has roots 3 and 2, I could do x minus 3 times x minus 2 times any scalar. And that would work. That would have those same roots. Scaling a polynomial by a constant doesn't affect the roots. But poly just assumes a leading coefficient of 1. So what that means, though, is that roots and poly, in a sense, are inverses of each other. So if I do roots, poly, 2 and 3, so I have 2 and 3, it constructs a polynomial that has roots 2 and 3, then it computes the roots of that. So it should bring me 2 and 3 back. And we see that it does. But I'm going to do a format long here so we can see more decimal places and take a look at that. So to this many decimal places, it says roots are 3 and 2. So that's what you would expect. But now if I do this, roots, poly, 1 through 5. So in other words, it's going to give me poly will give me the coefficients of a polynomial that has factorization x minus 1 times x minus 2 times x minus 3 times x minus 4 times x minus 5. And then it'll compute the roots of that. Roots will. So that should give me 1 to 5 back. And it almost does. So it's 1, 2, 3, 4, and 5, except for some round-off error. Not very much. I mean, these numbers are really close to 1, 2, 3, 4, 5. But in format, like if I had done format short, I wouldn't even know. Or wouldn't be able to see it. But here we can see that there's some round-off error. And it gets worse if I have a higher degree polynomial, like roots of poly 1 to 20 should give me 1 to 20, and it's a bit off. So notice here, only a few decimal places correct. It's more accurate down here, but as we get to the higher values, it's unacceptably off. This is called Wilkinson's example. So this is a famous example of how problematic it is to compute polynomial roots. You think it's something you take for granted, something that can be done easily. And for certain polynomials, like lower degree, yes, it can, but higher degree poses some problems. And if I do, let's go one step further, 1 to 50, it's so far off. We should have the numbers 1 through 50, real numbers, but we see we have no significant imaginary parts. And also really for way too large. So this was a complete disaster. It started all right, numbers that are close to 1, 2, 3, 4, 5, but even once we get to 6, it's a bit out of hand. So, oh well. We'll learn more about computing roots of functions towards the end of the semester. All right. Now, the next polynomial-related command I want to tell you about is a polyval. So if I'm going to make a polynomial, just a simple one, x squared. So 1, 0, 0. So this is for x squared. Polyval, you give it a polynomial, and you give it some x values. I'm just going to put in the x values 1 to 4, make it a column vector. And so all it does is it takes values in this entity, whether it's a scalar, vector, or matrix, whatever it is, whatever collection of numbers you have, and it will substitute those into the polynomial, and so the result is what is returned. So what we have here is 1 squared, 2 squared, 3 squared, 4 squared. So I gave it a column vector for x values. It outputs a column vector of y values. So the output always has the same dimensions as the input. So polyval is for polynomial evaluation at given points. Now, next we have more polynomial functions that perform calculus operations. So I'll make this polynomial again, x squared minus 5x plus 6. So a function polyder computes derivative. So given the coefficients of a polynomial, polyder computes the coefficients of a derivative. So a derivative of x squared minus 5x plus 6 is 2x minus 5. And sure enough, that's the polynomial that it outputs, 2x minus 5. Similarly, now I can take this polyint. This is for the antiderivative, or integral, as in the indefinite integral of a polynomial. So all these functions are doing, it's pretty straightforward. It's just applying a power rule for differentiation in polyder, and a power rule for integration. So since I took the derivative and I'm taking the antiderivative, you'd think, oh, it's going to bring me back to this polynomial, x squared minus 5x plus 6. But notice it's not quite there. The first two items match, 1 and the minus 5, but not to 6. The reason why is the indefinite integral of 2x minus 5 is not x squared minus 5x plus 6. It's x squared minus 5x plus c. C is an arbitrary constant. So MATLAB wants to output a unique answer, so it just makes a choice of that plus c always being 0. So if you take a polynomial, differentiate it using polyder, and then integrate it using polyint, it'll give you the same polynomial back except for the constant term. It'll always make it 0. Okay. Finally, for polynomial multiplication, and I'll make a simple examples here. Set p equal to x minus 5, and then another one be x plus 5. So we know that p times q would be x squared minus 25. So you can use the conv command to multiply polynomials. Conv is short for convolution, which is relevant to, for instance, Fourier transforms. Also, blurring blurring or smoothing content in the images. So we have, sure enough, x squared plus 0x minus 25. So it's called conv just because the main use of this function being convolution, but it happens to, but if conv is tried on row vectors that are coefficients of polynomials, it happens to compute the coefficients of their product. So conv serves, conv is like a dual purpose function in a way. So that's multiplying polynomials. But you have to be careful when adding polynomials. Now, P and Q are polynomials of the same degree. So if I add these, I'll get 2x by itself because the minus 5 and the 5 will cancel. So P plus Q, that's no problem, and sure enough I get 2x. But if I put P back to what I had before, x squared minus 5x plus 6, and I do P plus Q, MATLAB will give me an error because vector addition requires that the vectors have the same length. P has length 3, Q has only length 2. So if you're going to add row vectors that are coefficients of polynomials, just like any other row vector, to ensure they have the same length, you need to pad the shorter one with zeros to the left. So Q is one shorter than P, so I put a single 0 on the left, and now I get like x squared minus 5x plus 6, and then I add on x plus 5. So the sum of that would be x squared minus 5x plus x, so that's minus 4x, and then plus 6 and plus 5, that's plus 11. So sure enough, I get x squared minus 4x plus 11. In general, for adding polynomials, if we assume that the length of P is actually greater than or equal to the length of Q, you can do the following. P plus, and then I make to pad with a correct number of zeros. I have zeros. So I use a zeros function. Remember, zeros makes a matrix of a given size that's all zeros. So I want a matrix that has one row, and then the number of columns would be the difference in length. So length P minus length Q, followed by Q. So that would definitely work. If they're the same degree, then I'd have 0 zeros here, which is fine. It would just have only Q. But this assumption, length P greater or equal to length Q, is important. Otherwise, the roles of P and Q have to be switched. Okay. All right. Now I'm going to take some time to talk about number formatting. So if I set x equal to pi, right now I have format long, which I used earlier. The default format for number display is format short. It just displays 4 decimal places, whereas with format long, we have 15 decimal places. So that is format long that we see here. Format short, so there we have, like I said, 4 decimal places. Okay. Now, other formats. Format rat will take a number, which is a double precision floating point number, which we'll talk about more in Chapter 2, and try to convert it to the nearest fraction. Now, pi is a near rational number, but I just want to see what it does. 355 over 113. Now, if I go back to format long, out of curiosity, if I do 355 divided by 113, it does a pretty good job. So 3.14159.2 is the next decimal place of pi. Then it's 9 is the next place when it's supposed to be 6. So conversion to rational numbers using format rat does have some error in it. But for cases where you know that like a vector matrix is supposed to have nice fractions, then the format rat is helpful for displaying them. But yeah, sometimes in cases in my research, I've found that you can run a difficulty. You actually get the wrong fraction because of a round-off error once the numerator and denominator get pretty large. So it's something to be mindful of. But if I go back to format rat, so if I do something like this, 1 divided by, so here I'm doing dot divide. I'm going to make a vector of elements 2 through 5. Now if I do just 1 divided by 2 through 5, that would be an error because you can't, so division by vector is not defined. But if I just want to do component-wise division, take 1 and divide it by 2, and then 3, and then 4, and 5. So this will give me a vector 1/2, 1/3, 1/4, 1/5. And sure enough, because I have format rat, they're displayed as those fractions. Okay. Other formats, if you want scientific notation. Okay, so if I do, I'm going to make a number here, just something random. Okay. So here we have scientific notation with, so it's 2.3456 times 10 to the 4th. I can do format long, and I can use upper or lowercase e. Okay. All right, so that's strange. I thought that it would do lower or uppercase e no matter what. Okay, nope, sorry. I misremembered. So, well, it'll take little e or big E as a description of a format, but it'll always use lowercase e in actually expressing the number. Okay, other formats. We have format bank. So that's just 2 decimal places for dollars and cents. Okay, notice I've 0.3476, but it's going to round, as it always does for any of these numeric formats. And finally, one that isn't going to make much sense now, format hex. This takes the internal storage of a double precision floating point number and displays it using hexadecimal. Hexadecimal is base 16. So you have a digit 0 through 9, and then to account for 10 through 15, it uses the letters A through F. Now this won't make sense now, but when we get to section 2.2 on computer arithmetic, I will decipher this for you so that you'd actually be able to understand what this means, although it still is it's quite tedious to do so. Okay, so now I want to go back to format short and move on to the next item in the tutorial, anonymous functions. So if I want to make a variable that represents a function, because I can always implement a function in an M file, but suppose your function is very simple, like e to the sine 2x. It's rather cumbersome to make these one-line M files for functions like that, and you don't have to. So for this example, one I just mentioned, f of x is equal to the exponential of sine 2x. So the way I can define that as a function handle is f and then an @ sign to indicate function, and then you indicate the arguments in a listed closing parentheses, and then you follow that with what the function actually does. So exponential of sine 2 times x, and it tells me there's a function handle that has this value. So now I can plug in, like say, x equals 0. And that'll evaluate the function. So e to the sine of 0 is 0, so e to the 0 would be 1. Now, I could plug whatever into this function, because e or sine take scalars, vectors, matrices. So I could do f of. So if I have a vector of 5 numbers, a column vector of 5 numbers, and plug that into f, then it'll do that. So now I can make another example, x squared plus y squared. So this is a function of 2 arguments. So like I said before, I list them. I would make a list of arguments separated by commas. So I have square root x squared plus y squared. Now order is important. So whatever argument you pass first is going to be interpreted as x, and the other will be interpreted as y. So if I could do, for example, f2, 1. So I plug in x is 2, y is 1, so I get 4 plus 1 is 5, square root of 5, which is this. But here's where you have to be careful about defining anonymous functions. Make sure, if necessary, that your function is able to handle input arguments that are numbers, vectors, or matrices. So I'm going to make a vector here, x equals 2, 3, y equals 4, 5, 6, 6. So if I do this, f of x, y, that's going to give me an error because of the squaring. So MATLAB will not square a vector. It has to be a square matrix that you apply the exponentiation to. We saw this earlier when introducing graphics. So to fix this, I could do x dot squared and y dot squared. If I try it again, then it'll work. So be sure to vectorize your functions. Use dot operators where necessary, like for exponentiation or multiplication. If your function might take a vector as input, make sure your function is defined in a way so that it works for that vector. And therefore, it would also work for matrices. Like it'll apply your function to each entry of a matrix individually. So by vectorizing, it'll work for scalars, vectors, or matrices. There are certain MATLAB functions that accept a function handled as input. For example, MATLAB's integral function for evaluating definite integrals. The first argument you give it is your integrand. You have to make that function work on vectors. It has to be vectorized, or integral won't work. Okay, talk about other convenient functions. Okay, so I'm going to make a random matrix here, 3 by 2. So I could do like the size of A. So if I call size of A with two outputs, the first output will be set to the number of rows, second output being the number of columns. Also, I can just do this, size of A, by default, will return a row vector that has number of rows, number of columns. There are a lot of cases where you have a function that expects vector or matrix as input, and you don't know the size, but you need to get the size in order to perform a function's task. So often, one of the first things you'll do is get the size of whatever arguments you have. Okay. If I make a vector, so there's a column vector. Okay. So like if I do size of x, so it has 3 rows, 1 column. If it had been a row vector, it would be 1 row, 3 columns. But for length of vectors, I recommend using length of x. So that just gives you a single result. That's the number of elements in the vector. And this works the same way, whether it's for row or column vectors. So it ignores whatever singleton dimension and gives you the number of elements in the vector. I would not recommend using this for matrices. Like the length of A happens to be the number of rows. That's my curiosity. If I do the number, if I apply it to the transpose, it seems to be like the largest dimension. So this is A is 3 by 2, A transpose is 2 by 3. My advice, do not ever use length for matrices. Use size for matrices, length for vectors. Because then the result is intuitive. Okay, I shouldn't have made these all caps, but I was trying to emphasize, because you see here that these functions are in lowercase. You've been told. One useful function that works for vectors or matrices, so the total number of elements in any array, no matter how many dimensions it has, is num_l, so number of elements. That's short for. So A is a 3 by 2 matrix, so the total number of elements is 6. Okay. Now, suppose I have a matrix. So here's my matrix A here, and I want to morph it into a vector. So a reshape command does that. So if I do v equals reshape a, and I want to make it into a column vector. Well, a column vector would have however many elements are in the entire matrix, so num_L of A. So you specify what you're reshaping. Next is the number of rows, and then a number of columns. I want a column vector, so it'll have just one column. So there's my vector. Now notice how it placed the elements. Here, the first column goes first, followed by the second column. Okay. Now, so reshape uses what's called column major order, which is the same as Fortran. The reason for that is the lowest level code in MATLAB is actually implemented in Fortran. Fortran is the most efficient language still for mathematics. It may be the very first programming language ever created, but for straight up mathematics, it is the most efficient. So that's why MATLAB at its core is implemented in Fortran. So reshape uses column major order, whereas terrible typo there. Reshape uses column major order. Now, what if I wanted row major order? I could certainly do that for row major order, which is the same as like C and C++, for instance. Use a transpose. So if I do reshape a transpose, number of elements of A1. So look at the first row. It's 9745, 1337. So it puts the first row first, and then we look at the second row, and those elements go next, and so forth. So, so reshape column major by default, and row major if you use a transpose. Now, keep in mind, for reshape, the total number of elements cannot change, so your dimensions had to be compatible. You cannot take like a 5x5 matrix and reshape it into a 4x1 vector. It can only reshape it to a 25 element vector because that's how many elements are in a 5x5 matrix. So if you try something like that, MATLAB will give you an error and it'll tell you what I just said. Reshape, the total number of elements must not change. Now what's interesting about reshape is when it's used with a column major order, the way that the numbers are laid out in memory does not change at all. So reshape is actually a very efficient operation. It would just do a straight copy of those numbers. What changes is the way that they're indexed, because like if you're reshaping from a vector into a matrix or vice versa, so using like one index versus two. So only the indexing changes, but the actual memory layout does not. Whereas something like transpose is much more costly because you're actually moving all these numbers around. All right, we've actually gone past the point where I had any diary left over from class, because in class I kept going, but then once MATLAB crashed, the last few things I'd done in the diary had been lost. So I'm going to have to try to recreate the rest of what I did from memory, but don't worry, we're getting close to the end. So other convenient, if I can type here, other convenient functions. So here's, okay, so I have this vector x from before. So the sum of x, so if a vector, it just adds up all the elements of a vector, whether it's row or column. If I have a matrix, so I have this 3x2 matrix here, sum of a matrix does not sum all the elements of a matrix, it sums up each column. So it gives you so sum of a matrix gives a row vector consisting of column sums. Now that's the default usage. For one of the homework problems asks you to look at the help page for sum to try to produce opposite behavior. Like what if you want a column vector of the row sums? Now you could just work with a transpose, but sum has a way of doing that using the appropriate argument. Also, we have prod that works the same way. So if I have, I'll make a more interesting vector. Sum of the entry elements a vector that consists of the numbers 1 through 10. Okay, so the sum of x would be all that. But prod gives a product of all elements. Okay, so of course you may recognize that the product of all numbers from 1 to 10 is 10 factorial, which is what this is. So the usage of sum and prod is the same, it's just performing the appropriate operation, addition or multiplication. Okay. Now, next, saving and loading data. So I have all these variables here from this tutorial, and if I were to quit MATLAB now, then all those variables would be gone. But suppose I want to be able to bring them back for my next MATLAB session. So the way I could do that is using a save command. If I do save, so I give a file name that I just make up, like tutorial data. Now this is the simplest usage of save. You can look at the help page for other usages. So if I do this, notice at the top, tutorial data.mat. So .mat, so it's a MATLAB.mat file that holds MATLAB variables. It is a binary file. Do not try to look at it in a text editor. It'll just look like garbage. But that saves all of the values of all your variables and their names. So everything you need to know about the variables is kept there. So now this command clear would wipe out all these variables. It cleans out the workspace. It's a very destructive command, so use it responsibly. So clear, bam, everything's gone. But now what I can do is load tutorial data, and it's all back. So yes, indeed, a very scary command to use, but if you do what I just did here, you'll be fine. Okay. And finally, circumstances that led to the crash from before. Actually, I just realized I can go here for my command history from what I did last time to make sure I run the same commands except for the one that led to the crash. Just make sure I didn't forget to do anything. Okay, we're good. So I'm going to create a couple. So first, measuring efficiency, at least in terms of time. So I'm going to create some random matrices here. This is a 1,000 by 1,000 matrix, and B is another random 1,000 by 1,000 matrix. So if I do this, tick, and then compute the product of these matrices, and then talk. Okay. So it didn't take very long, so 0.0665 seconds. So tick starts the clock when you perform your operation, and then talk stops the clock and reports the time. Now, if I save a value of talk in a variable instead, if I want to use that time later, then it won't print any message. But when there's no outputs to talk, then it will print this. And out of curiosity, I'm going to do it again. The time varies, but notice here it can be significantly faster. So it depends on what else your computer is doing. A lot of times with more complex code than this, like your code from your M files, what I've found is that if you run it and time it and then do it again, sometimes it can be noticeably faster because MATLAB will try to optimize code on the fly when it runs it the first time, so that subsequent executions turn out to be somewhat faster. It's not something huge, but noticeable. Okay. Now that didn't take very long. So what happened last time was I made larger matrices. I made 100,000 by 100,000. And MATLAB crash. So I'm not going to do that this time. I'm not going to lose this video again. So there's a 10,000 by 10,000. And then the next matrix, I'm going to make it smaller. It has to have 10,000 rows, but I'm going to give it fewer columns, like just 1,000. Yeah, only 1,000. So A and B before had 1,000,000 entries each. So A is 100 million, and B has 10 million. So if I do C, so if I do the same thing as before, A times B, it will take some time. I promise you it will finish. It won't crash me because I actually did, I did 10,000 by 10,000 before starting this video, and that was fine. That took about 30 seconds. So we see it's quite a bit more because of the larger size. Okay. So as an example, I was showing you earlier, if I save talk in a variable, this will take about 5 seconds, as we see. So it doesn't print that same message here because I have no semicolon. It just prints out the value of multi time. I can hear my computer revving. It's not liking what I've had to do apparently. So I'm going to quit while I'm ahead here. Diary off. Save that diary, and I should have an intact video. So time to bring this to an end. All right, so I'll see you in class on Tuesday.